We present Gaussian mapping for evolving scenes, the first online Gaussian splatting framework designed for the long-term reconstruction of evolving environments. Traditional online 3D GS reconstruction systems take an RGBD stream as input. They iteratively grow and optimize a global 3D map using photometric losses across keyframes. The map is then used for novel view synthesis. However, real-world scenes may undergo structural changes outside the camera's field of view during the capture. This unobserved dynamic behavior breaks traditional iterative optimization for two reasons. First, it corrupts the existing 3D GS map. Second, it uses keyframes observing conflicting scene states, which stalls the optimization. To resolve map corruption, we introduce a dynamic scene adaptation mechanism, or DSA, that handles object additions, removals, and movements. We model object motion as a combination of removal and addition. Treating the current frame as ground truth, we detect changes where the rendered depth is closer to the camera and the color deviates significantly from the observation. We segment splats from the high-error 2D area, render them to all co-visible keyframes, and use SAM masks to capture complete object silhouettes. Later, majority voting across keyframes allows us to accurately segment all the splats representing the removed object and remove them from the map. On the slide, you can see that even if we detect only part of the bed as disappeared, DSA allows us to detect the whole object and remove it from the map. For newly added objects, we initialize new splats in the area where the rendered depth exceeds the observed depth. We later on use them in the keyframe management system. To prevent these structural changes from disrupting the optimization process, we propose a keyframe management system which, instead of discarding entire frames and losing valuable data, aggressively masks out only the regions corresponding to newly added or removed splats within co-visible keyframes. If a keyframe accumulates a masked area that is too large, it is entirely excluded from the optimization. Here is our complete pipeline. Given an RGBD stream, the system identifies keyframes and triggers the dynamic adaptation module to handle newly appeared or removed objects and update the global map. Our keyframe management system then masks or discards the conflicting keyframes, ensuring that only geometrically consistent observations are used to optimize the final 3D GS map. Quantitatively, our method significantly outperforms baseline approaches on both input and novel view synthesis, demonstrating superior metrics in both color and depth rendering. Importantly, these performance improvements generalize to real-world datasets, where structural changes are much subtler and harder to track. We conclude with a demo video comparing our approach against recent 3D GS reconstruction systems. Thank you for your attention.